Hello and welcome to this video lesson. In this video lesson, we will be looking at two examples on forces, focusing on second and third law of motion. In this question, we're asked to calculate the tension force between box A and box B. Let's look at the situation. We have box C here, which is a 7 kilogram object. It's attached by a string or a rope to box B here, which is 2 kilograms, and that box is attached by a rope to this box over here, which is 5 kilograms. The rope is going through a frictionless pulley here, so this pulley isn't actually rotating, it's just frictionless. And there's actually no force of friction between the table and the box. Thinking about the forces here, this box is being pulled by the tension force. There's nothing stopping it because there's no force of friction. Box A here is being pulled by force of gravity or gravitational force. But being pulled back by box B, or the tension between box B and box A. Box B is being pulled down by box A's tension by the gravitational force, and it's being pulled back by box C here. So basically there are two objects that are experiencing the gravitational force. This one over here, it's kind of causing an inertia, which is resisting the motion of the whole system from going down. And because of it, we can see that if this mass was higher, based on first law of motion, the change in motion would be resisted more, so the total acceleration of the system would be less. And if this mass was less, the inertia of the system would be lower, and therefore the resistance to change would be less, meaning the acceleration would be higher, or these forces would cause a higher acceleration. To analyze this question and to find the friction here, we need to draw a few force diagrams. We can do this in many different ways. We can draw a force diagram for everything and use those to find the acceleration and the tension force, or we can just think about this carefully and see if there's any more efficient way. In this case, we know that the whole object is accelerating in this direction. So this box is accelerating this way, and these two boxes are accelerating this way. I'm going to use a green marker to show that this is acceleration this way, this is acceleration this way. So we can kind of assume that this is one system, because this is frictionless pulley, so this is one system attached to B, attached to A, and everything is accelerating in just one direction. And based on that, we can actually draw a force diagram. In this force diagram, we're going to have our system, which is mass A, mass B, and mass C. And we are going to have our dot here, and we are going to assume that everything is accelerating downwards in this case. So this is the force of gravity, and that's actually it. There's only one force acting on it, and this force is caused, the only two masses that are actually experiencing gravity are mass A and mass B, and that multiplied by the gravitational acceleration will equal to the force of gravity. And the total mass of our system here, so mass total of this system over here is 7 plus 2 plus 5, which is 14 kilograms. We know that based on second law of motion, there's only the net force is in the downward direction, so the acceleration will also be downwards. So let's write a net force for this system over here, F net, and I'm going to take down to be positive. F net is equal to the sum of forces. In this case, there's only one force acting on my system, that's Fg, and that's equal to mass times acceleration for the system. My gravitational force, as I have stated above, is ma plus mb multiplied by the gravitational acceleration, and that's equal to the total mass. I'm going to write this as mt multiplied by the acceleration of the whole system. ma plus mb, that's 5 plus 2, that's 7, times gravitational acceleration. I'm going to take that as 9.8 in this question. And the total mass is 14 kilograms. And we're trying to find the acceleration from this. And we also know that all of this system, so everything in this system is attached. Therefore, whatever A is experiencing in terms of acceleration, it's the same thing that B is experiencing, and it's the same thing that C is experiencing. And that's why we can put this as one whole system. Okay, let's continue. 7 times 9.8 gives us 68.6, and that's equal to 14a. So a will equal to 68.6 divided by 14, which is same as 4.9 meters per second squared. And I know that my direction is downwards, but the answer that I got is positive, and I've taken down to be positive as well. Based on this result, I know that this box C is accelerating in this direction at 4.9 meters per second squared, and both boxes A and B are also accelerating in this direction or downwards at 4.9 meters per second squared. I found what my acceleration for the whole system is, or what every object is experiencing in terms of their acceleration, and that makes it a lot easier to calculate for the tension force between A and B. To find this tension force, I need either a force diagram on A or a force diagram on B. I would prefer to do A because the forces acting on A are less than forces are acting on B. So let's do that. Let's draw a force diagram on A, and I will do that with orange. So my system is now mass A, and the forces acting on it, so there's one force going downwards, that's force of gravity. In this case, that's equivalent to mass A times the gravitational force. I can just write it here, don't have to. And there's also one other force that's pulling my system upwards. I know that it's not as big in terms of magnitude because I have a downward acceleration. And this force is the tension force caused from mass B to mass A. So the way I usually write my notations is I write what kind of force it is. In this case, it's a tension force, and is caused from object B on object A. And basically, based on third law of motion, I would know that this object also has a downward force, which is opposite in direction to the upwards force, but the same magnitude as this force over here, because that's what the third law states. I'm going to write a net force on my object here, and I'm going to take down to be positive for my net force. And the sum of forces in this case going downwards, one of them is Fg, and opposite to that is the force of tension from B to A, and that will equal to mass times acceleration. My system is A, so I need that mass and its acceleration. Okay, I know my Fg in this case is mass A times gravitational force. So I'll write that down. Minus FTBA is equal to mass of A times the acceleration. And now I'm going to plug in all my values. I know the mass of A is 5. Gravitational acceleration is 9.8. I'm trying to find this tension force over here, so I don't know what it is at the moment. This is 5, and I have found my acceleration as 4.9 meters per second squared. Continuing my calculations, 5 times 9.8 is 49, and 49 minus F of tension from B to A is equal to 24.5, and if I were to rearrange everything, my tension force will end up being 24.5 newtons. And basically, based on the numbers that I've given, I have this number, and this number. They're all given to me as two significant figures, so my final answer is only accurate to two significant figures, and therefore my tension force is equal to the force of tension between B and A, and that's approximately 25 newtons to the correct number of significant figures. In the second question, I have a juicier version of the first question, and this is a little bit more complicated. I got a frictional force of 50 Newton now that acts on box C, pulling it backwards. And what I'm trying to do is calculate the tension force between box A and B again. So last time I didn't have any frictional force, so it was a little bit easier. This time I have to calculate it using adding that frictional force. And there's a second part of the question which says calculate the total distance that box C travels. So this is going to be interesting. Let's talk about how we're going to solve this question. If you want to try it out first, and then we'll go over the solution. Very similar to the last question, boxes B and A are going to experience an acceleration force in this direction if they were to accelerate, and we have to figure if they are or not. And this box C will be accelerating in this direction. The whole system can be modeled as 1 because the object can be accelerating all in this direction or the downward direction. It doesn't really matter which way we say they're moving, but they're all accelerating, they're all connected to one system, and therefore we can treat them as one system. We're going to have our system as mass A, mass B, and mass C, and the total weight on this is, the total mass is going to be 7 plus 2 plus 5, which is 14 kilograms. And I'm going to assume that my system is accelerating downwards, and there's now going to be a force of gravity, which is caused by mass A and mass B's gravitational force, and there's going to be a resistive force on box C, which is going to be pulling it back. This is force of friction, and we know what the value of that is. That's 50 Newton. So I'll write it down in my diagram. It just makes my calculations, it'll just make it easier for me as I'm walking through my solution. I know that the force of gravity, I'm assuming that the force of gravitation is slightly bigger, and just estimating it, I got 5 plus 2, which is 7 here. Gravitational force, let's say approximately 10, 7 times 10, approximately 70, which means it's going to be bigger than this. We are going to take G as 9.8, but that was just an estimation. And that will give us an idea that the acceleration is going downwards. Let's write the net force equation to find the acceleration of our system, F net. I'm going to take down to be positive, and I'm going to highlight it. And the forces acting are Fg in the positive direction and force of friction in the negative direction, and that's equal to the total mass times the acceleration based on the second law of motion. Gravitational force in this case is ma plus mb, that's 7, times the gravitational acceleration, that's 9.8, minus the force of friction, which is 50, and that's equal to the total mass, which is 14, times acceleration. Let's put in some numbers. This is 68.6 minus 50, and that's 14a. So 14a will equal to 18.6, and divide everything by 14, and I will get 1.32857 dot dot dot, and I'm going to keep the exact value in my calculator for future calculations. I need to find the tension force between B and A. I'm going to do exactly what I did in the last question, and that is to draw a force diagram on box A. So box A will be experiencing, this is system is mass A. Box A will experience a gravitational force pulling it down, and that's mass A times the gravitational acceleration. And it's going to have a tension force caused from box B on it. So I've labeled all my forces. There's nothing else interacting with box A. So I can write my net force. I'm going to take down to be positive here. That's MAG, or the gravitational force, minus the tension force. And that's going to be equal to the mass of A times its acceleration. Let's plug in some numbers. Mass A is 5. This is 9.8 minus the tension force is equal to 5, which is mass A, times its acceleration, which I found to be 1.333. I'll write, but I'll use the exact value on my calculator. And once I plug everything into my calculator and rearrange everything, I will get the tension force at 42.357 dot dot dot. My numbers are only good to 2 significant figures, so my final tension force is going to be approximately 42 newtons. You can see that based on the solution, comparing to the last question where there was no force of friction on box C, the acceleration is much less because of the force of friction, which is slowing down our system, and also the tension force here has also increased. This tension force will also be increased to overcome that frictional force that's been added to the system. Let's now look at the second part of the question. In this second part, we have to find the total distance that box C travels. So now we really have to think about the problem very carefully and really analyze what's happening. Okay, the first thing that's happening is there's a force of acceleration of approximately 1.33 meters per second squared, which causes all of these bodies to fall. As these objects are falling, this is going to fall for a distance of about 1 meter. And once this falls, let's say this rope is very small, so we're going to make a little assumption that the length of this rope is negligible compared to this length. So we're going to assume that when this falls, B is going to fall on it really quickly, and by that time box C has moved approximately a distance of 1 meter. So that's the first part of the movement of box C. During this time, it is accelerating at a rate of 1.33 meters per second squared. When it will, let's say if it started from rest, it's going to gain some final velocity here. Let's say this is stage 1 and stage 2 is after it has accelerated for a distance of 1 meter. and that's when these two things aren't acting on it anymore, and there's no more gravitational force by boxes A and B. Then the only force that's going to be acting on it from that stage, stage 2, to its last stage where it stops, is the frictional force. And we have to see how much does that frictional force slows it down, and what kind of acceleration does it give to box C, and what distance it travels during that time. So let's actually draw a system diagram of what's happening now. And I'm just going to leave this value A here for now because we're going to need it a little bit later. I'm going to draw a nice system diagram. I'm going to do it let's do it in black. So this is only box C because that's what we're considering now. We know that box C is going to travel for about a distance of 1 meter at an acceleration of 1.32857, and again I'm using the exact value throughout this whole calculation, and it's going to keep going, and let's say this is stage 1 and this is stage 2, and it's going to have velocity 1 is going to equal to 0, velocity 2 is going to be unknown, we don't know it yet. We do know that the distance traveled during this time is 1 meter, and again we are making an estimation we are making an assumption that the rope between A and B, its length is very, very, very small. After this, stage 2, when it's accelerated for the 1 meter, then the masses A and B no longer have an effect on it. So the only force acting on it then is the force of friction. So at some point, there's nothing else pulling it forward, so it's only going to be pulled backwards. So it's actually going to stop. So at some point, it will have a velocity of 0. We don't know what the acceleration on it is going to be, so we have to figure that out, and then we got to figure out what is this distance over here. So there's a few information that we need to find. One is the second velocity here. One we can find based on the force diagram on it is the acceleration here. And after that, we can find what this distance is and add the two distances to get the total distance that the body traveled. I'm going to pull this up a little bit. And we have a nice system diagram, and we're going to work from there. I'm going to label everything else in my diagram as well. Time here is unknown, and unknown here. And the acceleration, we know that acceleration is going to be backwards because it is slowing down, so I'll label it as this direction for now. Again, you can also use the other direction. Let's start with a force diagram for stages 2 and 3, or between stages 2 and 3. The object, mass C, is experiencing a force of the normal force. It's going to experience the gravitational force, and it's going to have a 15 Newton force of friction on it. So that force is still acting on it. That force is basically just caused by the two surfaces touching, the surface of the table and the surface of the box. So now I can write an F net, and I'm going to take left to be positive. In this direction, there's only force of friction acting, and I'm doing X direction again. Force of friction, and that's going to equal to the mass of the system, and this is system is mc. This is the mass of the system multiplied by its acceleration. Force of friction is 50, mass c is 7, and this is acceleration. and the acceleration is 50 divided by 7, which is 7.142857, and it keeps going, and I'm going to use that exact value for the rest of my calculations, and it's going in the left direction, and that's the same value here, so I'm going to write this as 7.14 meters per second squared. Okay, so now I have my values, and let's look at the first stage to second stage. First stage, it is at rest. It's going to accelerate at this rate for a distance of 1 meter. I have 3 pieces of information, so I can find the second velocity. And once I have the second velocity between stages 2 and 3, I have this velocity, or I'm going to calculate this velocity. I have the acceleration now, and I have the final velocity, and therefore I can find the displacement between stage 2 and 3. Let's do that. Let's find this velocity first. Okay, between stages 1 and 2, I'll use the color of green. So this is stage 1 to 2, and I'm going to use the equation v2 squared is equal to v1 squared plus 2a delta d. And then I'll put my vector signs, and I have to choose a coordinate system. I'm going to take right to be positive here. So v2 is what I'm trying to calculate, is equal to v1, which is 0. Oh, that's very nice, plus 2. My acceleration is 1.328, and my displacement is 1. And if I put that on my calculator, I get v2 as plus or minus 1.63 meters per second. And I'm going to take the positive value because I know it's traveling to the right, so therefore v2 is equal to approximately 1.63, and I'll use the exact value for my answers, meters per second to the right. For the other stage, which is 2 to 3, I'm going to use the exact same equation because I still don't have delta t. So that's, and I will take again right to be positive. So v2 squared is equal to v1 squared plus 2a delta d, and this time I'm trying to find delta d. So v2, oh sorry, this is v3 and this is v2, and my displacement here is displacement from 2 to 3, so I will label that as well. And this one over here was displacement 1 to 2. Okay, back to this one. v3 here is 0 because it's going to stop. v2 I calculated as 1.63 squared plus 2a. I have my a value, that's negative 7.14, and delta d is what I'm trying to find, so that's delta d from stage 2 to 3. Okay, I'm going to do some calculation here, so I get delta d 3 is equal to 2.657 divided by 2 times negative 7.14, and I will end up getting, if I put that on my calculator, I get 0.186 meters, and it's a positive value, so I know that it's going in the right direction. The question is asking for the total displacement, so the total displacement is equal to the displacement from stage 1 to 3. That's the displacement from 1 to 2 plus the displacement 2 to 3. And I have those values. One of them is 1 meter. That's given to me in the question. And the other one is 0.186. I know that this 0.186 is actually, well, it doesn't actually really matter how many significant figures. I know this 1 is given to me as 1.0. And when you add two numbers, you always have to leave it to the least number of decimal places. So 1 plus 0.186 will equal to 1.186, but approximated to 1.2 meters in the direction right. And it's asking for the, let's just go back to the question just to check. The question is asking for the total distance and not the total displacement. So basically for the total distance, we don't even need a direction. So our total distance is, and here I was actually calculating the displacement, so I'm going to put, it doesn't really matter displacement or distance. My total distance is equal to 1.2 meters, and this is an approximation, so I'll put an approximation sign and I will box my answer.